Okay, this is 7.2. Take out your notes for 7.2 exponential equations. So it's going to build on what we already had last chapter. We did y equals a times b to the x. The first part is kind of review. First thing in your notes, make sure it says b is not equal to 1. I think that's wrong in your notes. Make that change. And this just says if b to the x equals b to the y, if the bases are the same, you can set the exponents equal to one another, and it goes fairly swiftly. 5 to the x equals 5 to the third. Drop, it's got to be x equals 3. This one right here, 6 to the x equals 216 is 6 to the third. So you're changing them to get the bases to be the same. X equals 3. Not bad. Next one, 25 to the x minus 1 equals 5. The first thing I would do is change 25 to 5 squared. 5 squared to the x minus 1 equals 5. Now if you're raising a power to a power, we multiply. So it's 5 to the, now you got to distribute 2x minus 2 equals 5. Now this is 5 to the first power. So again, I've got the bases the same. Set the exponents equal to one another. 2x minus 2 equals 1. 2x equals, I'm going to add 2. Add 2. 3. X is 3 over 2, or 1.5. So you're just getting the bases to equal one another. And then you set the exponents equal to each other, and you're good. This is 12 to the 2x plus 3 equals 144 is 12 squared. What's the problem we're going to solve? 2x plus 3 equals 2. 2x equals negative 1. X is negative 1/2. Plug it back in if you're not sure. 2 times negative 1/2 is negative 1 plus 3 is 2. 12 squared is 144. I might have to do a little calculator work to figure out, they're not going to give you one that isn't a base of 6 here. So it's 6 to the x minus 4 equals 1296 is 6 to the 4th. Might have to do a little trial and error there. X minus 4 equals 4. X is 8. I don't think that's too hard of a concept to get the bases to equal one another and solve the exponents. We're back to some word problems with our y equals a times b to the x. We're going to write an exponential equation. Remember, population problems can be population at time t. These are not any different. Initial population, we write p naught times 1 plus r to the t, where r is the growth rate. If it's decay, then r is probably less than 1, or they tell us that, then we subtract. The a and the p naught are the same. The b and the 1 plus r are the same. It says write an exponential equation describing the firm's growth. He now, after 7 years, he has 393 clients. That's my population at time t. He started with 23 clients. I'm just going to do this as b to the 7th. Do we know how to solve an equation like this? Certainly. Divide by 23. B to the 7th equals, what's 393 divided by 23? $17.09 approximately. 17.09. Hey, what did we do last chapter? How do you undo b to the 7th? You could take the 7th root, or we could raise it to the power of 1/7. 1/7. So we can take our answer that's on our calculator and raise it to the 1/7. So we've got our 17.0869 whatever, and we're raising it to the power of 1/7. I got 1.5. Did anybody get 1.5? So that's going to be my growth rate. Really, if you think about it as R, 1 plus R, he's gaining 50% per year. So we write our equation then. His number of clients at time t will be equal to, he started with 23 and he's increasing by half as many each year. That could be a t, that could be an x. You could write his number of clients as c at time t, that would work. Now could we make a prediction? How many clients will he expect to have at year 20? Just plug in 20 and you're good to go. So we want to remember our exponential growth equations. Kristen starts experimenting with 7,500 bacteria cells. That sounds like an initial population. After 4 hours, time t, this is going to be p after 4 hours. There are 2,300. Write an exponential function that can be used to model the number of bacterial after x hours. So I'm going to do 23,000 equals 7,500 times b to the 4th. Take your 23,000 divided by 7,500, 3.06 equals b to the 4th. Raise that to the power of 1/4. I got 1.32. Now, if you round, your last answer here may be slightly different. My equation now is y equals initial times the base raised to the x. How many bacteria after 12 hours? Population after 12 hours. 7,500, 1.32 to the 12th. If I just use the number that was in my calculator, I get, without rounding, 216,302.22. If I just use the 1.32, I'm going to get a slightly different answer. I got 209,869. I think this is a good example of when you round something, you bring in some error and then you raise it to the 12th power. There's a fairly significant difference in those two answers. 7,000 bacteria or so. And either of those answers would be acceptable. Hopefully the y equals a times b to the x problems are all right for you. Now, don't get alarmed by this formula, because if you compare it to the two formulas that we just had, y equals a times b to the x, or population at time t equals initial population 1 plus r to the t. Remember, these are the same formulas. Now we're going to add compound interest to the formula, and we're going to say amount at time t is equal to p times 1 plus r over n to the n times t. Here's what we have. Principal. The principal is p. That's the initial investment, initial population, value of a. These things all mean the same thing. Instead of 1 plus r, we have 1 plus r over n, and instead of t, we have n times t. It's very important that you understand n is the number of times per year that we compound the interest. So if we're just compounding once a year, then the formula is exactly the same as the population growth. But if we're going to compound it quarterly, quarterly means we're going to compound 4 times, once in March, once in June, once in September, and once in December. If we're going to compound monthly, we would be at 12. So you're often going to hear quarterly, and if you get quarterly, that's going to mean n is equal to 4. 4 goes there, 4 goes there. Monthly, monthly, N will be 12. Weekly, 52 is what they use. Daily, 365. So what we're doing is we're taking our interest rate and we're dividing it up and spacing it out 4 times or 12 times. So we have to cut our interest rate that many in order to have it. The interest rate is always per year. So this one here says we're going to 10%, but we're going to take our 10% and we're going to divide it equally over 4 times. So 10% divided by 4 is 2.5%. But we're also going to do it 7 years. But if it's 4 times per year, then there's 28 compoundings that take place. So if I was to write this equation, it says Alex invested $1,200 at an interest rate of 10% compounded quarterly. Determine the value of her investments in 7 years. Amount after 7 years. Her principal was $1,200. 1 plus, you got to change your percents to decimals. 0.1 divided by 4 raised to the 4 times 7, or 28th. So really my problem is 1,200 times 1.025 to the 28th. Why 0.025? 10% spaced out equally 4 times. 10%, 10 divided by 4, 2.5. And then if I'm doing it 4 times for 7 years, 28 times it gets done. Type this into your calculator. 1,200 times 1.025 raised to the 28th. Alex has hit the jackpot. Alex will have $2,395.79. Don't spend it all in one place. Again, the formulas are very similar. Please recognize the similarities. Your life will get easier. An investment account pays 5.4%. That's R. And I'm going to make it 0.054 compounded quarterly. We should get an N is 4. We should have done a different one. $4,000 is the initial investment or principal. Find the balance after 8 years. T equals 8. P is 4,000. Amount after 8 years is equal to the principal times 1 plus 0.054 divided by 4 raised to the 4 times 8, or 32. You can type that whole thing in your calculator if you don't want to do that. 1 plus R over N. You can just type in straight 4,000. Just put it in parentheses. 1 plus 0.054 divided by 4. Raise that whole thing to the 32nd. And presto, you've got yourself, after 8 years, $6,143.56. Isn't that wonderful? Okay, that's it. So you can continue working on your homework. Have a wonderful day and a better tomorrow.